What's up, everyone? How's it going? Today we are going to talk about the arterial circulation, the arterial system. So today we're sort of going to introduce the major functions of the arterial system and then talk about how the arterial system serves as this hydraulic filter in order to keep up the continuous flow of blood and in order to maintain regulation of our cardiovascular system. So the arterial system has many different functions, and so some of the major functions include the regulation of blood pressure. And so we talked about how our arterioles, depending on what environment we're in, what sort of activities we're undergoing, can change their radius due to the contraction of smooth muscles that surround them. And so the primary means to regulate resistance and then therefore blood pressure regulation is through the size of our arterioles. And so it has a major role in regulating our blood pressure. When arterioles are vasoconstricted, that helps to increase resistance, which increases blood pressure. But when arterioles vasodilate, that lowers resistance, overall total peripheral resistance, and then lowers blood pressure, mean arterial pressure as well. The second major function of the arterial system is the distribution of blood volume. Remember that the blood is leaving the left side of the heart and entering this arterial circulation throughout the body. And ultimately, the size, again, of those arterioles are going to dictate how much blood is passing along through to the capillaries of certain organs, and then therefore how much blood is heading towards the venous circulation. And so the arterial system basically dictates how much blood is going to be shipped out and delivered to all these areas of the body, just again based on the size of those arterioles and how much resistance to blood flow there is. A third major function is the regulation of cardiac performance. And I want you to sort of keep this note in your head right now because it's a very important concept as far as all of cardiovascular physiology is concerned. Changes in the heart will affect the vasculature, and the changes in the vasculature will affect the heart. These are two interdependent parts of our cardiovascular system, and constantly there are changes going on in each which are going to impact our pressure, resistance, cardiac output. And so the arterial system, in a way, is going to regulate the stroke volume and then therefore the cardiac output of our heart. We already talked about afterload, and so when there is a high resistance to blood flow on the arterial side, when there is a high pressure, it can limit stroke volume in that direction. But we also have to keep in mind that, again, stemming off from the last point, that the arterial circulation, the size of those arterioles, are going to dictate how much blood passes through. And so if there's not a lot of blood flow going from the arterial side to the capillaries to the venous side, well then less of that venous blood is going to return back to the heart. And we already talked about that and the consequences then that is going to have on preload and diastolic volume, and then therefore stroke volume and cardiac output. So again, if these arterioles on the arterial circulation are more vasoconstricted, less blood passes through, and then therefore less blood makes it back to the heart, which limits stroke volume and cardiac output, because the heart can't pump out blood when it doesn't have enough to pump out. The heart cannot pump what it does not receive. Last, another major function of our arterial system is to regulate our core temperature. And so when core temperatures increase, there is vasodilation to the arterioles of the skin. This helps produce sweat, and we lose some of that heat. But then when we get cold, when there's a lower core temperature, we vasoconstrict those vessels. That warm blood stays closer to our internal organs, and that helps to keep up core temperature. Now remember, the heart is going to go through cycles. It has a period of relaxation, diastole, where it's not pumping out blood to the rest of the body, and then it has a period of systole, where it is increasing pressures and then delivering out blood. So that's why it is an intermittent pump. However, regardless of the phase of the heart, we need a continuous, steady flow of blood through the large arteries to the arterioles and to the capillaries, so there can be that exchange of nutrients and O2 for CO2 and different waste products. And so a continuous, steady flow of blood helps to achieve that and helps to regulate our physiology. So the aorta and the large arteries have a lot of elastic connective tissue. And you combine that with the high resistance arterioles, these are going to act together as a hydraulic filter. What's going to happen, instead of having this intermittent flow of blood that's based on the phase of the heart, we're going to have a steady, continuous flow of blood throughout the cardiovascular system. So what we see right away in the aorta is when that left ventricle ejects out blood. Since the aorta, that vessel is very elastic and has a lot of elastic fibers to it, what is going to happen is that blood is going to stretch out that aorta. And being that, again, it is elastic, that is going to then snap back. And that force and pressure that comes from that elastic component of the aorta is going to help drive blood flow continuously forward to the capillaries. When you have a loss of compliance or increased arterial stiffness, what's going to happen is that you lose some of that elastic component, and then therefore you're going to have reductions in blood flow during diastole. Now, most of the blood flow does occur during systole. However, again, we need this continuous flow of blood, and so in order to maintain cardiovascular function, we want healthy elastic arteries. And so now, aging you can avoid, and arterial stiffness does increase with age. And then, other lifestyle factors like diet and exercise ultimately can affect that arterial stiffness as well. And so that's why, we try to reduce things like atherosclerosis, or that plaque that develops within our arteries, because ultimately, by trying to improve someone's diet and physical activity, we're helping to improve their cardiovascular health and helping to keep up the basic functions of our cardiovascular system. The left ventricle is going to eject out blood into the aorta. And when you have a healthy aorta and healthy arteries, again, they have a major component of elastic connective tissue, a lot of elastic fibers. So what happens is there are two types of energy that are created. The left ventricle is going to create that pressure in order to help drive and propel blood forward towards the capillaries. But then also some potential energy, some stored energy is created due to the elastic nature of the aorta and the large arteries. And so what happens is that blood is going to stretch out those arteries, and that energy is stored within the walls. And then when the heart closes, what you are going to get is recoil. And so now some of that blood now that was in the arterial side is going to be propelled forward during diastole. So again, you're getting this continuous flow of blood regardless of the phase of the heart. Let's say though you have an individual that has developed really bad lifestyle behaviors. They have had a bad diet for decades. They haven't been physically active. They smoke. Likely what's going to happen is that they are going to develop atherosclerosis and arterial stiffness. And so that arterial stiffness is going to lead to negative consequences as far as blood flow is concerned. During systole, that left ventricle is going to eject out blood. But when you have these rigid arteries, that arterial blood, that stroke volume that is coming from the left ventricle, there's going to be a limited amount that is stored within that arterial system. And really another major outcome too is that we're losing that potential energy. We're losing that elastic component, and therefore losing the benefits of flow that we get from that recoil. And so during diastole, what we are going to see is that blood flow is going to decrease. And so we don't get that recoil, we don't get that continuous movement of blood flow. And so again, it becomes more of this intermittent blood flow that's dependent upon the contraction of the left ventricle. interval, as opposed to continuous blood flow, regardless of the phase of the heart that we see in those with healthy arteries. Ultimately, the compliance of the arteries is going to make it easier on the heart. And so we're going to talk about how this hydraulic filter helps reduce cardiac workload. And so work can be defined as force times distance in general physics, but when you work out the math, basically, as far as the cardiovascular system is concerned, we can equate it to pressure times volume. So if we have a continuous flow pump, which is not one like our heart is more of an intermittent. If we had a continuous flow pump with a resistance of 1 and a pressure of 100, ultimately, the outflow of this continuous flow pump is going to be 100 milliliters per second. So that's 100 milliliters flowing out then every second. And if you quantified the work, pressure times volume, you basically get 10,000 mmHg milliliter each second, right? And so now let's compare that to then an intermittent pump. But first, an intermittent pump like our heart with rigid tubes. And so this intermittent pump is producing 200 milliliters for half a second when it is active. Think about systole. And then it's producing nothing during the last half, the other half a second, right? And so when you have a rigid tube, right, this resistance is going to be the same as the first one, just to make things equal. But basically what you get as far as outflow is concerned is 200 milliliters per second. But remember, this is only going for half a second. During that second phase, because you have this rigid tube, you don't have that continuous flow of blood. So overall, again, you're getting 100 milliliters for that entire second. But look at the work that has been developed during this phase. You get double the workload for the same amount of fluid, or in our case, blood outflow, right? So you get this intermittent blood flow, and ultimately you have to work harder for it. But now, if you have this intermittent pump with compliant tubing, right? If you had compliant arteries, basically we're going to get the same output, 200 milliliters per second for that half a second. And so what's going to happen though now is because this tubing is compliant, is elastic, it's going to create a constant pressure and a constant flow of blood that's independent upon the phase of the pump. And so again, resistance is the same. The outflow that you get overall is going to be 100 milliliters per second. It is the same for all three. But again, with this intermittent pump, you are getting a workload that is half of one with rigid tubes, or in our case, rigid arteries, and is the same or similar to this continuous flow pump. So overall, having these elastic, compliant arteries helps reduce our cardiac workload. So a problem with arterial stiffness is that the heart is working harder to produce the same amount of stroke volume. And therefore, if that left ventricle is working harder, if those cardiac muscles are working more, well, then you need to supply more oxygen in order to keep up with that increased energy demand. Just as you wouldn't like to go to a store and pay 50% more on something when you didn't need to, the body doesn't like to spend extra energy on its functions. And so when you have this increased arterial stiffness, that's what you are seeing, that you're having to consume your cardiac muscle is having to consume more oxygen at a given stroke volume in order to keep up with this demand. And so we are spending more energy to pump the same amount of blood. As far as cardiovascular health is concerned, we should be worried about arterial compliance, because just as we said, that is going to have an impact on our cardiac workload. And so, we could measure compliance using the slope of pressure volume curves. It's important to note that this graph here looks different than pressure volume curves we've seen in the past. When we looked at that for the heart, these axes were reversed. But ultimately, looking at the differences between pressure and volume give us a sense of compliance. And when we have a steeper slope, we have a high compliance, and this gives us information about how much blood volume is stored for a given change in pressure. And so what you're seeing here is the results from, after autopsies, the aorta were removed from these different aged individuals and then compared based on pressure and volume. And what you could see is that compliance is reduced in these aortas with advancing age. And so ultimately, what does that tell us? As we get older and this arterial stiffness increases, these older age groups are going to have increases in cardiac workload, right? They're going to need to produce more energy for the same amount of stroke volume. And sometimes, that could lead to further complications and, things like fatigue and heart failure if this progresses to a certain extent. And so again, us as health professionals, we're concerned about cardiovascular health, want to promote these nice diets and good physical activity and exercise regimens in order to prevent things like this from occurring, or at least, to slow down all the negative effects that come with aging. It's important to note that compliance is reduced at high pressures, and think about this in the sense of a balloon. It's easier to fill up that balloon sort of in the middle of blowing it up. And as you get to, higher and higher pressures within, as that balloon's really filling up, it gets harder and harder to expand that balloon. So that relationship in the slope and in the curve, you're seeing both at low pressures and high pressures that you have that reduced compliance. But, again, in healthy young individuals, you're going to see this increased compliancy in the aortas than compared to older individuals. That will conclude part 1 of the arterial system. Today we talked about the major functions of the arterial system, the importance of arterial compliance, and how it will regulate blood flow and cardiac workload. In the next lecture, we'll talk a little bit more about mean arterial pressure, which is, again, the primary regulated variable of the cardiovascular system. And then, therefore, since we're talking about mean arterial pressure, we're going to discuss a little bit more about cardiac output and the determinants of cardiac output, and a little bit more about total peripheral resistance. Thank you guys so much, and I'll see you next lecture.